So let's begin with this particular topic. Let's go to the next slide and also I'll pick my pointer. So this is something we had already seen in the last lecture, where I had defined energy in terms of the C VDD square multiplied by the N, and here N is represents the number of the switching in a time interval of T. So what it is actually coming from the energy term, which is nothing but C VDD square, and I can write it as F switching multiplied by the time or the region, the time duration of interest, right? So this particular factor of F switching multiplied by time T gives us the number of the switching, right? So this F switching can also be rewritten in the form of alpha and then the F clock, right? Where alpha is nothing but the activity factor multiplied by the F clock. And then the product of alpha, F clock, and the duration of interest will give me the number of switching. All right. And, we want to define this particular energy term as energy delivered by the VDD for a particular task. So what we are trying to perceive or, read as an energy delivered for completing a particular task. And then when we are talking about a particular task, we can always relate it to the number of the switching that the task performs at the output nodes, right? It could be many output nodes, or it could be a single output node in a large digital circuit design. But if I can characterize a particular task to be completed with such and such number of the switching in the specific nodes, or in all the nodes, or in one particular node, then I think we can actually define the energy delivered by the VDD for a particular task. And that's what we are going to look into this particular lecture, where we will consider the task completion for to see the impact of DVFS on the energy term. Right. Remember that DVFS is basically a technique to reduce the energy that is required for the completion of the task. So we will try to evaluate how much of energy that has been reduced, or it has been saved, or how much of energy benefits we will get using the DVFS technique. Right. So coming back to this particular energy term, which we have arrived from the F switching multiplied by T, we can also have it as a function of number of the switching in the time interval of T. And if I actually divide it by the time interval T and then multiply by T, this N by T is nothing but the number of switching per unit time. We can also call this as nothing but the rate. So the rate of the switching, or for a particular task, we can also define the rates. So if it is the rate of 100%, that means that we need whatever number of switching in that particular time duration. That will say that it's 100% of rate. Or in an absolute way, we can also say that, okay, it is, the 10 switching per 10 seconds. So it is nothing but one switching per 1 second, so that we can also define the rate in terms of the number of switching per second. But generally, this rate is basically a normalized value. So for example, if I have a lot of tasks, if I have a task A, if I have a task B, if I have a task C, and then so on. And each of this task is defined by, a rate in terms of the absolute value, where I need 10 switching to be done in, let's say, 1 second. And then 10, or rather, I'll say B task is 20 switching in 1 second, and the C task will be nothing but 100 switching in 1 second. And then so on, right? So what I mean by the normalized factor is you have one more column where we take, we consider the maximum of this, which turns out to be, in this particular case, C task is having 100 switching per second, and then use that to normalize all other tasks. So in this case, the rate for the task C is 1, the rate for the task B is 0.2, the rate for the task A is 1, because I'm actually dividing the 10 with that of the 100, the maximum value. So I'm basically having a normalized value here. So a normalized value of 0.1, 0.2, and 1. So normally we'll see that the rate will not go beyond 1. So it will be there in between 0 to 1, right? So in that sense, it's a normalized value, and then if I do a multiplication of T, I should be able to get the energy factor, and then finally, if I multiply that with the maximum, the rate of switching for a given set of tasks, then I can find out the absolute energy value. Right. So in this particular term of energy, if you can notice that it is actually a function of, or I have written it as a function of VDD, the rail voltage, and it is a function of the rate. And remember that the rate is nothing but the number of switchings per unit time, and it is a function of basically F switching. Right, so because N is actually defined as the product of the F switching multiplied by T, a product of F switching and T. So, and F switching is nothing but, it is related to the F clock. So basically the rate is actually dependent on the F clock, the frequency of the clock frequency. And what I mean is, if, VDD and rate are decreased by half, the energy naturally decreases by 1/8, because energy is directly proportional to the square of VDD. So if the VDD rail voltage is decreased by half, instead of 1 volts, if I have a rail voltage of 0.5, I will get the energy to be decreased by 1/4. And the rate, if it is decreased by half, that means that the clock frequency somewhere it is kind of switching to a half the clock frequency, and thereby my energy is going to decrease by half the times due to the rate getting decreased by half. So put together, if I actually decrease VDD rail voltage as well as the rate by half, I'll actually get the energy to be decreased by 1/8, right? Which is a huge energy savings, right? Now, what do you mean by getting the rate to be lowered, right? So let's say that I have a time duration of, let's say, 10 seconds. So I have this as a 10 seconds. And let's say for task A, so I'm going to say that task A requires 10 switching to be done in 10 seconds. So this is starting from 0 second, this is starting and ending at 10 seconds. So generally, I'm actually 10 seconds is too high in a VLSI design in today's technology node. It should be in terms of nanoseconds or even go to an extent of picoseconds. But just to understand, make it very, very simple, I'm using the seconds unit instead of the nanoseconds or picoseconds. So if I choose the task A, and let's say that the task A needs 10 switching to be done in 10 seconds. So in each of in each of the 1 second, in each of the 1 second interval, 3, 4, 5, and then 6, 7, 8, 9, and then 10 seconds, it is going to do a switching at each of this time interval, and then thereby it completes, right? It completes its task, right? And so the energy required for the task A here, I'm going to write it as C VDD square, and then the rate for 10 seconds. So the rate is, I'll say that 1 switching per 1 second. So 1 switching per 1 second multiplied by the duration of interest is 10 seconds. So this will be my energy that will be, expended for completing the task A. Now let's say that for task B, I have again the same, 10 seconds window. But task B is requires, it has, let's say that it has 10 seconds of time duration, but it requires only 6 switchings to be done, right? So if I actually pick the interval 2, 3, and then 4, 5, and then 6, 7, 8, and 9, and this is my 10 second. Right, so although it is not divided linearly, but in that sense, what I'm saying is in each of these intervals of 1 second, right, the switching we require is only 6 switching, so it can actually delay its switching, or rather it can have a reduced rate. So the switching can come here, and then I require only 6 switchings to be done, and then finally it arrives here. So I have 6 switchings, the switching number 1, the switching number 2, switching number 3, 4, 5, and 6 in 10 seconds. So my rate is now actually 0.6 as that of the previous one, right? Here the rate I have considered to be the maximum, so the normalized value is actually 1. So my energy for this particular task B, right, will be nothing but C VDD square and multiplied by 0.6, and then of course 10 seconds. So 0.6 switching per second, and then multiplied by 10 seconds. So naturally my energy is going to decrease, right? What DVFS says is, whenever I am changing the rate or whenever I am changing the clock, so as to adjust the rate, right, at the same time, can I actually change the voltage rates, right? And if I actually do, instead of 0.6 rate, as well as, instead of only 0.6 rate, as well as if I do a rail voltage change of 0.6, then I'm going to have a drastic change in the energy. All right, hope this is clear. So if I actually apply DVFS, then I am going to have C multiplied by 0.6 VDD the whole square multiplied by 0.6 into whatever the time t. So it is going to give me 0.216 C VDD square multiplied by t of 10 seconds. And if I compare with this, it is going to give me a naturally close to 80% of the energy savings, right? Moving forward, so let's take some few more instances where the rates are different, and let's see what happens. So as we know, that energy is nothing but C VDD square multiplied by rate into time t. Let's say for a task A, we need to have the rate is configured to 1. So rate multiplied by time t, t is the duration for which we are kind of probing the energy, the overall energy. So 1 into t is what is required, or rather, the rate multiplied by t is equal to 1 into t. So I will have an energy term of C VDD square 1 multiplied by t. Let's say that for a task A, right, for the same task A, instead of rate to be configured as 1, if I actually do a configuration of 0.6, then rate multiplied by t, right, will be different in the sense if the task A requires 10 switching to be done in 10 seconds, and let's say that the rate is 1 switching per 1 second, right, in this particular case, then it requires 10 seconds to complete the 10 switching, right? Similarly, for the rate is 0.6 here, so my t, the rate multiplied by t, which will give me the 10 seconds, or rather the 10 switchings here, right? So the rate has been decreased now, so this t has to be increased, so that's what I'm doing. So I require 1 into t, which will give me 10 switchings. 0.6 into t1 should give me the 10 seconds, or rather the 10 switchings. So my t1 should naturally increase if I'm using a lower rate, right, just to complete the task A. Similarly for task A, if rate has been increased, then the number of switching can be accommodated in a lower amount of duration of time. So if it is increased to 2, then my t1, the duration of for the task A to complete 10 switchings will be nothing but 0.5 into t. All right, so let's try to have a look at it one by one. So what I meant in the previous slide is, let's say I have the 10 seconds of duration, so 0 to 10 seconds. Right, for the task A, which is now configured with a rate of, let's say 1, that means that 1 switching per second. So I will have 1 switching to be done at each of these seconds, and then it will require, let's say that it requires 10 switchings to be done. So it will complete, the task A will complete in 10 seconds. So the energy for the task A, so all these are task A here in this particular case, so task A. So the energy that required to complete the task A with a rate of 1, right, will be nothing but C VDD square. Rate is 1 multiplied by time, which is nothing but 10 seconds, right? Now, if I actually decrease the rate, right, for the 10 seconds, now decreasing the rate implies that I need to have, in fact, the number of switching, or rather the rate of switching is going to be lower. So it will have only 6 switchings, 1, 2, 3, 4, 5, and then the switchings to be done in 10 seconds. But I require 10 switchings to be done. So it will have to extend beyond this. And whenever it does complete 10 switching, so this will be the 10 switching. So it will be extended up till here. Right, and then the way it will extend is it will be 5 by 3 times extension of the 10 seconds. So my energy for the rate for completing task A with a rate configured to 0.6 will be nothing but C VDD square, right? And then the rate will be 0.6, but it will have an extension of time 5 by 3 into 10 seconds. It turns out that 0.6 is nothing but 3 by 5, and then this is 5 by 3. So this will get cancelled with that of this. So I'm finally having C VDD square multiplied by 10 seconds, right? Which is same as that of the energy with the rate of 1. Again, if I have one more case where the rate is doubled, and then let's say that this is 10 seconds. The rate is doubled in the sense the rate is now, the rate is 2 now. That means that I will have now more switching. So I will have a switching of 10 switching. So 3, 4, 5, 6, 7, 8, 9, and then 10. And this is the task A is completed, right? Exactly in the 5 second. So now the energy that is estimated for the rate is equal to, 2 is nothing but C VDD square multiplied by the rate of 2. And then now I will have 10 seconds divided by 2, or 0.5 multiplied by 10 seconds. So this 2 and this 2 will get cancelled, and I will have C VDD square and multiplied by 10 seconds. Right. So what this example says is, if task A is to be completed within this particular duration, I can actually increase the rate, decrease the rate, right? And based on the number of the switching, it is going to complete, right? So the energy, if I don't change the rails at all, based on the change in the rates, then I'm not going to get any kind of benefits, right? But for the same thing, whenever the rate is 1, if I change the VDD here, for a rate of 1, I will get, 1 VDD. So I'll get C VDD square 1 multiplied by 10 seconds. But here, if I actually change, because the rate is now changed to 0.6, and if the VDD is also changed to 0.6, I'm actually getting 80% of benefits of the energy as that of the first case. Similarly, and if I actually change, the rate, if it is 2 times, then I'll have to have a 2 VDD square, then it's going to have more energy, right, than that of whatever is seen here. Right, and then if I want to compare, then I need to compare that with respect to, the time interval of, the same time interval. Right, whichever is ending first, I'll have to use the same time interval. So in this case, I'll have to compare, in the 5 seconds window, what is the energy that has been compensated here, energy compensated here, energy compensated here, and then try to extract or try to see what is the energy at that particular time window of 5 seconds. Right, so naturally, whenever the rate is lower, and if I can actually have a lower rail voltage, naturally that particular energy component will give me a lot of benefits, energy benefits, right, going forward. So what we are saying is, if I have only, the change in rates, it will not give that much of benefits in the energy. But somehow if the rate can be directly proportional to the VDD, if the change in the rate will have a change in the VDD, it's a linear relationship. That means if the rate is changed, right, and then the VDD also changes, then I will have a larger energy savings, a larger impact on the energy benefits. So change in the rate needs a change in the VDD. If we can configure that way, then for example, task B, a rate of 0.6 is needed to complete. Right, what it really means is I need 6 switching in 10 seconds. Let's say that is an example. Then I can have this 0.6 rate multiplied by time t. So my overall energy in this particular case for duration of 10 seconds, and for this overall duration of 10 seconds, if I can maintain a rail voltage of 0.6 VDD, I'll get an energy of 0.216 C VDD square multiplied by t, which will give me a 78.4% reduction in the energy if it was, the C VDD square into T, right? If I was actually doing the task B with a rate of 1, right, and then going up till 10 seconds, it will give me the energy of C VDD square multiplied by T, right? So in that sense, it is going to give me a reduction of energy in 78.4%. Right, going to the next one, moving ahead. So what we are saying is the rate, whenever we want to plan our rate, the switching rates for completing a task, right, we will also change the VDD in a linear relationship, right? So if the rate tomorrow for task A, if it is 0.39 the rate is required, then if the rate of 0.39 is required, then my VDD should also be 0.39, right? 0.39 volts. And if day after tomorrow, if I want to change this 0.39 to, let's say, 0.49, my VDD value should also be 0.49 volts. But remember that the rail voltages in a digital design, we actually cannot get so much of rail voltages available. Right, the rail voltages, the different rail voltages are available in the form of a voltage divider, but we don't want to have a lot of rail voltages available. Otherwise, it will occupy its own space. So we'll have the space occupied by the rail voltages itself, and it will not have enough space to design our circuits. Right. So in that sense, what we don't want is a continuously analog values of the rail voltage going from 0 to 1 volts. Right, but what we can do is we can have some specific rail voltages, 2 or 3 levels of VDDs, right? 0.5 VDD or 0.75 VDD, right? Or maybe a 1 VDD or 1.2 VDD, or very few select VDD rails could be made available, and we can try to accommodate the task completion by using those specific VDD rails and then configuring the rate according to the VDD rails that are available, right? So if I have a VDD rail of 0.8, then why not configure the task completion with 0.8 of the rate? If I have a VDD of 0.5, then why not accommodate the rate of 0.5, right? The other disadvantages is continuously changing the VDD for the rate requires the prediction of the task parameters. So if, let's say, the task A is there, and after that task B is there, and after that task C, and then so on, those tasks are listed. So what we need to do is, if I know predefined parameters of the tasks for task A, B, C, and D. So if I know that task A needs a switching rate of 1 per second, and task B requires 0.6 per second, task C will require 0.69 per second, then I need to have a characterization or a prediction of the task parameters, and then I need to change the rate. Changing the rate will require a continuous changing of the clock frequencies. Remember that the rate was a function of the clock frequencies, and the clock frequencies changing we have to do using the phase lock loops, so PLLs. So we will require an extensive hardware design, and this this again occupies the space, and having this extensive hardware design is kind of a big overhead. So instead of doing that, why not have a deterred levels? Deterred levels means having a specific levels, having a specific rail levels, and then configuring the rate according to those specific rail voltages that are available, right? So what I mean is, if I have a specific rail of 0.5 VDD and 0.75 VDD, then for any task, whether it is task A, B, C, D, and whatever up till Z task, right? If I can configure the rate of switching to 0.5 of match with that of the VDDs, and then for a 0.75 VDD, if I can have configure the rate of switching to be 0.75 so that it matches with that of 0.75 VDD, and then try to accomplish that particular task, right? So in this particular example, so what I've done is, we want to achieve, let's say for task A, if we want to achieve 0.6 of the switching rate, that to be completed in a time duration of T. Now the question is, can it be achieved by, these two deterred levels, these two levels of 0.5 rail and 0.5 rate, and 0.75 voltage, and then the rate of 0.75 and a rail voltage of 0.75. right? So let me draw a diagram here. So what we need to achieve is, I'm taking the same example of 0 to t is equal to 10 seconds, right? Ideally, we wanted 6 switchings to be done in the 10 seconds. But let's say that the 0.6 VDD is not available in our design, right? So, but we have 0.5 VDD and 0.75 VDD. That means that I can actually choose the switching rate of 0.5 and I can choose a switching rate of 0.75 because it matches, it gets aligned with that of 0.5 rail VDD rail and 0.75 VDD rail. So in that case, what we are saying is, if I need 6 switchings to be done in 10 seconds, why can't I use the 0.5 rate? So 0.5 rate means it is pretty slow, right? Slower than that of the 0.6. So I will have one switching here. I will have, one switching here. I will have one switching here. And then I will switch into 0.75 switching rate, right? So I need 6 switching. So what I will do is I will have a faster switching now, right? So this will be 0.75 and then this will be configured to 0.5 switching rate. So I'm going to write it as 0.5 rate and then 0.75 rate, right? Because we need to achieve 0.6 rate overall in 10 seconds. That means that I need to complete 6 number of switchings in 10 seconds. So why can't I use a slower rate, right? Slower rate initially and then a faster rate finally, or the otherwise I can also have 0.75 rate initially and then go slow to 0.5 rate and then complete the 6 number of switchings in 10 seconds, right? So what it means is the number of switching by using these two deterred levels, by using these two rates, it still should match with the total number of switching. So the total number of switching is still 0.6 multiplied by t, right? And that should match with that of our 2 different configured rates, switching rates. One is 0.5 multiplied by whatever the duration it takes, t1, plus 0.75 multiplied by t2. This t1 and t2 is our, the time on the time domain. So how much of amount of time the 0.5 rate is configured and how much amount of time the 0.75 rate is configured. Right, so if in that sense, I will have this particular equation. So 0.5 T1 plus 0.75 T2 should give me the total number of switching. And we know that this T1 plus T2 should be equal to that of the 10 seconds. In this case, it is T. So we have 2 equations. We have 2 variables or unknowns, T1 and T2. So I should be able to get this T1 and T2 in terms of the value T. So I'll get 0.4 T and 0.6 T for T2 and T1 variables. Right, hope this is clear. So what we have done in this particular slide is, we want to configure the 0.6 rate for a particular task, right? But because 0.6 configuration, the rate configuration and its rail voltages are not available, so we will use 0.5 rate, configure it, the task for 0.5 for some amount of time t1, and then switch to 0.75 rate, right, for the t2 interval, right, which will sufficiently give me the 6 number of switchings in 10 seconds. Right, so what I've done is I've written a table here, the computation time, the rate, and then the VDD rail. So if I'm choosing the 0.5 rate here, right, I need to choose 0.5 VDD and 0.75 rate here, then I'll have to choose the 0.75 VDD because this will give me the DVFS, the voltage as well as the rate or the frequency switching. Right, so the dynamic voltage frequency switching, of course, we will, this is called as a deterred level DVFS. The reason it is called deterring is because we don't have all the rail voltages available with us. So we have only specific levels of VDD, and that is why we say that it is kind of truncated or it is a deterred DVFS. Right, so if I'm using a rate of 0.5, I will require the time interval of 0.6 t, and if I use 0.75 after that, then the time interval is 0.4 t. So what it really means is to achieve a rate of 0.6 for a duration of t, right, we will have to use 0.5 rate for 0.6 t duration and 0.75 rate for 0.4 t. So my overall energy now is nothing but the addition, is nothing but the accumulation of this particular energy and the accumulation of this particular energy. So which is nothing but C into 0.5 VDD square multiplied by 0.5 is the rate multiplied by 0.6 T plus C into 0.75 VDD the whole square multiplied by 0.75 multiplied by 0.4 T. So the overall energy turns out to be 0.24375 C VDD square multiplied by T. And if I actually compare with that of the 0.6, right, it used to give me 0.216 C VDD square. So this particular term is not at all a bad term. It's not at all a bad value because it is very, very close to 0.216. And if I really look into this with respect to a task A, which was doing actually C VDD square, which used a rail voltage of 1 and then a rate of 1, it actually gave me 75.62% reduction in energy when compared to a rail voltage of 1 VDD and then a rate of 1. Right? And if I use the DVFS, if I use a DVFS here, so this will be my 0.216 because I had the rate of 0.6, so the VDD has to be 0.6, so it gave me 0.216. Right, so with respect to this, with respect to 0.216, this 0.24375, right, actually gives us the benefit of 96.45% benefits of the DVFS. Benefits in the sense, so if I calculate this energy of DVFS, it is 0.216 C VDD square into T. So when compared to the task A of 1 VDD and 1 rate, it was C VDD square into T. So I had a benefit of how much? 78. So let me have a quick look at it. So it gave me 78.4. So 78.4%. And this one is giving me 75.62. So if I actually compare 75.62% with that of 78.4%, it is actually giving me 96%. So although this is a deterred DVFS technique, right, this particular energy term is giving the benefit of almost 96.45% benefits of what we can achieve in DVFS. But with DVFS, it is, if you use an analog value, so like whatever is the rate, we will use the same VDD. The problem there is we have to have an extra hardware or an hardware overhead. So that was one of the issues, and that's why we went into the deterred levels, which is very, very suitable for our digital design in terms of saving the space as well as giving almost close to 96.45% benefits of the DVFS technique. So hope it is clear. Moving on to the next one, let's say that the two deterred levels we have is 0.5 VDD and 1 VDD instead of 0.75 VDD. And we have to achieve 0.6 rate multiplied by T. So that means that the same example of 6 switchings in 10 seconds. So I have to use the 0.5 VDD rail. That means that I have to use a rate of 0.5 and then 1 VDD, then I have to use a rate of 1. So what it means is here in from 0 to 10 seconds, I can choose to have a 0.5 rate. So I will have a very slow switching, right? It could be whatever the number of switchings. And then finally, we will have a very fast switching because a rate of 1 is there. So this particular rate will come at the end, and then this particular 0.5 rate will come in the beginning or vice versa. Right? So in this particular, this will be T1 and then this one will be T2. So I need to find out T1 and T2. So I have two equations, 0.5 T1 plus 1 T2 is equal to 0.6 T, and then T1 plus T2 is equal to T. So I should be able to find out what is T1 and what is T2. Turns out to be 0.8 and 0.2. And so if I put it in a table of a rate of 0.5 and 0.5 VDD, a rate of 1 using a 1 VDD rail. So this time interval is 0.8 T and 0.2 T. And if I try to find out, this is the energy 1 and energy 2, this is the total energy for completing the task, the task with, to achieve the number of switchings as 6 per 10 seconds. That means to achieve a rate of 0.6, I will have this energy E1 plus E2. And that is what we are achieving, 0.5 VDD, the whole square multiplied by 0.5 multiplied by 0.8 T C plus VDD square 1 into 0.2 T into C. So overall, we are achieving 0.3 VDD square into C into T, which is actually achieved 70% with respect to our the overall savings in energy if we were to use one VDD rail and a rate of 1. Even for this task, which requires a rate of 0.6. And in addition to that, it gives actually 90% benefits of the DVFS. 90% benefits means with respect to this, if 2.216 C VDD square multiplied by T, right? So we are getting 78.4% of benefits here. Here we are getting 70%. So 70% divided by 78.4% is going to give me 90%. So we are actually using a deterred DVFS with the two rails of 0.5 VDD and 1 VDD, and that is actually giving us 90% of benefits of DVFS, right? So hope you are able to understand this. So I have given two examples having the deterred DVFS, dynamic voltage frequency scaling, where rate is directly proportional to the rail voltage. So if I want to configure a particular task, right, for a particular rate, switching rate, then I will also choose that particular VDD rail, right? Now the question is, how do we choose that particular, or if we, as a designer, we have an ability to select what particular, or we have as a designer, we have an ability to design a particular rails. Now the designing of the rails actually comes from the characteristics. So for a particular design, if we want, if we have n number of tasks, task A, B, C, and so on, right? And then if we have a rates to be designed, let's say 0.6 is the rate for a task A, 0.5 is the rate for task B, 0.75, and then so on. So we will have to choose the particular rail voltage, right? Particular rail voltage. It could be either 0.6 VDD and 0.75 VDD, right? It could be those two rails, or three rails, or maybe another set of rails, which will give me a maximum energy benefits for performing all the tasks, right? So the rail voltage design is actually coming from the characteristics of this n number of tasks, which is going to use the VLSI design, which is going to use our design, right? Whatever design we have done on one particular part of the chip. And for completing the task, and if we are using that particular design, then we need to calibrate or characterize those tasks, and what should be the the rate for that. Based on that rate information, the switching rate information, we should be able to design the optimal design of the rail voltages, right? And then this could be applied for for all the tasks. All right, so hope this is clear. So what we have learned in this particular lecture is the dynamic voltage frequency scaling. What it really implies is, if we are changing the rate to complete a particular task, then the rail voltage should also be changed so as to get a maximum energy benefits. But having different values of VDD is not possible in a large higher order digital design, because we will not have multiple rail voltages. What we will have is specific rail voltages, and that is where the deterred DVFS technique is very, very useful, which is also giving us the benefits very, very close to the benefit of the natural DVFS technique.